In this series of videos, you will be learning about processes taking place in the nucleus of an atom. And this field is called nuclear chemistry. Aside from these processes, you will also learn how to compute for the rates of these processes, their so-called half-lives, their effective half-lives, and their biological half-lives. As you know, the reference I used is a book on nuclear medicine. So we will take this field of nuclear chemistry in the context of radioactive atoms that are used in hospitals, or some of them might be used as drugs. Now, nuclear chemistry, again, involve processes taking place in the nucleus of an atom, which is totally different from the chemistry that we know. Chemical reactions, as defined, involve rearrangement of atoms from one molecule to another. So, how can an atom from one molecule move to another molecule? So, this is possible if the atom breaks one or more covalent bonds and then forms one or more new covalent bonds in the second molecule. And what do we have in covalent bonds? We have electrons. So in chemical reactions, your electrons are involved. But in nuclear reactions, your protons and nucleus are the ones that are primarily involved. Another main difference between nuclear chemistry and or nuclear reactions and chemical reactions is the amount of energy involved. Nuclear reactions involve massive amounts of energy, while chemical reactions relatively absorb or release small amounts of energy. So, if we look at some chemical reactions, we notice that the highest we can go is in the range of kilojoules per mole. But in nuclear reactions, we can reach higher than that. That is why we use some of these nuclear reactions as source of energy. Now, aside from learning about these nuclear processes, you will also learn how to compute for the rates of these nuclear reactions, their so-called half-lives, their effective half-lives, their biological half-lives, and also you will learn how to compute for what we call dosage. So this is in the context of nuclear medicine, radioactive atoms used in hospitals, in imaging, in diagnosis, and in treatment. First, we need to recall our representation of an atom. So to represent an atom, especially in nuclear reactions, we must show the atomic number and the mass number of a specific atom. So recall, you have the symbol. So SY here is not an element. I just use it like a general symbol. On the upper left side of your symbol, you write your mass number. So again, we determine the mass number by adding the number of protons and the number of neutrons. Meanwhile, on the lower left side of your symbol, you write the atomic number. And the atomic number is equal to the number of protons. And again, your atomic number defines or determines the identity of your element or atom. So which element is that specific atom? It depends on the atomic number. So here are some examples. And you notice that they are paired, right? And in each pair, you will notice something. For example, let's look at the first pair. What do you notice in the first pair? Notice that they have the same mass number. They are different elements because they have different atomic numbers, but they have the same mass number. So, atoms with the same mass number but different atomic numbers are called isobars. So, these two atoms are isobars. Next, let's look at the second pair. Notice that they have the same atomic number, hence, both of them are carbon atoms, but they differ in the mass number. So, this carbon has a mass number of 12, so it's carbon 12. Meanwhile, this carbon has a mass number of 13, so it's called carbon 13. So, another way to write them would look like this and like this. And you guessed it right. So when you have two atoms with the same atomic number but different mass number, they are called isotopes. Finally, let's look at the last pair. At first glance, you will notice that there is nothing similar about these two. But recall that we determine the mass number by adding the number of protons represented by P plus the number of neutrons represented by N. Your atomic number is determined by the number of protons, which means that if we subtract your atomic number from the mass number, we get the number of neutrons. So, how many neutrons do we have in nitrogen 13? It's 6, right? How many neutrons do we have in oxygen 14? It's also 6. So there is also a term used to describe such pair of atoms, and they are called isotones. Okay, so if you have the same number of protons, meaning same atomic number, then they are called isotopes. If you have the same number of neutrons, then they are called isotones. And if you have the same mass number, they are called isobars. Now, there is a collective term for your neutrons and your protons. So they are called nucleons. So whenever you see the term nucleon, it would refer to a particle in the nucleus. So it can be a neutron or it can be a proton. Now, interestingly, there is a theory, and this theory is supported by evidence, experimental evidence, okay, regarding the arrangement of your nucleons in the nucleus. So they postulate that the nucleons are stacked in what we call nuclear shells, much like your electron shells. Well, they are not exactly shells, but we refer to them as orbitals. But we picture them as shells around your nucleus. Just like your electrons, your nucleons are occupying these so-called nuclear shells. And just like your electron shells, the innermost shell is stable if there are two electrons. The second shell from the nucleus is stable if there are 8 electrons, and so on. There are also numbers of nucleons in each nuclear shell that, if satisfied, will make the nucleus more stable. So these numbers are what we call magic numbers in nuclear chemistry. So whenever you find these magic numbers as the number of protons or the number of neutrons, okay, It means that that atom, specifically the nucleus of that atom, is relatively stable. It will not undergo any nuclear process further because it's already stable. So, again, if the number of protons or the number of neutrons in your atom, either one of them, is equal to one of these magic numbers, that nucleus is particularly stable and the atom does not undergo any nuclear reaction. In fact, it is better if the number of protons and the number of neutrons, both of them, are equal to these magic numbers. So you might ask, or you might connect this statement to the fact that those atoms that undergo nuclear processes are unstable. They have nuclei that are not stable. And they want to achieve this stability by changing the number of protons and the number of neutrons in their nucleus until they reach the so called magic numbers. These magic numbers are, in fact, even. It is very rare for a magic number to be an odd number. Now, we will not dive deeper into this theory. For this subject, it is enough for you to know that there are what we call nuclear shells in the nucleus of an atom. And these nuclear shells can explain why we have the so called magic numbers. Now, imagine your nucleus is made up of protons, which are positively charged, and neutrons, which are neutral. They don't possess any charge. You would think that wouldn't the protons repel because they all have the same charge? That is in fact true. But their repulsion is prevented by the presence of the neutrons. So the neutrons provide the so called strong forces inside the nucleus, and this prevents the protons from repelling each other, hence maintaining the structure of your nucleus. So, um, nucleons are also defined by what we call binding energy. Okay, so this binding energy depends on the specific atom that you are looking at. Okay, so you can have carbon 12, which has 12 nucleons, right? 6 protons and 6 neutrons. And you have carbon 13, which has 13 nucleons, 6 protons, and 7 neutrons. So the protons and neutrons in carbon 12, each of them will possess a certain value for its binding energy. And that specific value will be different in carbon 13. Now, if we look at the range of the values of your binding energies for all known atoms, including isotopes, all isotopes of an element, the range would be 5 to 8 mega electron volt. And this is a very large number. It means it's 5 million electron volts to 8 million electron volts. Take note, your electrons only need energies in the kilo electron volt range to be removed from an atom. But you need 1,000 times more of this energy to remove a proton or a neutron from a nucleus. Now, we see a different term here. We see the term nuclide. What does a nuclide mean? So, a nuclide would refer to a specific atom with a specific number of protons and specific number of neutrons. That's it. Now, if this nuclide is radioactive, then we can call it radionuclide. But if it doesn't undergo radioactivity, it's simply called a nuclide. So, a while ago, we saw this representation of carbon 12. So this is a nuclide of carbon 12. And we saw xenon 131. I forgot the atomic number. Let's go back to that slide. 54. This is a nuclide as well. And if this nuclide undergoes some radioactive process or some nuclear reaction, then we call it a radionuclide. As an example, we have here rubidium 86. So rubidium 86 can undergo a specific type of nuclear reaction called beta emission. You will learn about this in another video. So beta emission. So in this process, 1.77 mega electron volt of energy is involved. And your rubidium gets turned into strontium. So you notice the atomic number from 37 decreased to 36. Now, what is this 89%? It means that in your population of rubidium atoms, 89% of the atoms will be transformed into strontium 86. Rubidium here is called the parent nuclide, while strontium is called the daughter nuclide. And we can represent the reaction like this. So we have 86, which is the mass number, and 37 as the atomic number. And we have the products plus a beta particle. No. It's like this, forming strontium. Okay. So we will learn again in a different video more about these nuclear reactions, okay? For now, you just have to remember or focus on the terms parent nuclide and daughter nuclide, okay? And the fact that in a population of a certain radionuclide, not all of the atoms will undergo the same radioactive process. So what happens to the remaining 11%? So you notice here, there is another arrow pointing, okay, to another energy level. And it says there 11%. So this means that 11% of our rubidium 86 undergoes a different pathway. So it's the same. It's beta, okay? A beta particle is involved as shown here. And the energy involved is 0.7 mega electron volts. Okay. Now, after reaching this specific energy level, you see a squiggly line. And when you see a squiggly line, it means that energy is released. Okay. So in this second pathway, what is actually happening is that this process is taking place. However, so you are forming the strontium daughter nuclide here. But this strontium daughter nuclide is still in an excited state. So we have what we call an excited state of a certain nuclide, okay? And since we have this squiggly line, it means that this strontium that is in its excited state releases the excess energy. And if you notice, the energy is 1.07 mega electron volts. So if we add the two, we still get the 1.77 mega electron volts from the first pathway. Okay, now there is a typo here. So this shouldn't be beta, but the manner by which an excited nuclide releases the excess energy is what we call gamma radiation or release of gamma rays. Okay, so again, If you have a population of a certain radioactive or radionuclide, okay, a fraction of this population undergoes one pathway to form the daughter nuclide, and the rest of the population undergoes a different pathway. It still forms the same daughter nuclide, but the only difference is that in the second pathway, it first forms the excited daughter nuclide, and then the excited daughter nuclide releases the excess energy through the release of gamma rays or through gamma radiation. If you notice here, um, in the first step, we have 11%, right? So this is still consistent. We add this with 89%, we get 100%. But when the excited daughter nuclide releases the excess energy, only 8.8%, which means that you have a remaining fraction of your atoms, your strontium atoms, that remains in an excited state. Now, again, this is just an average. This is just in the macroscopic scale. In nuclear chemistry, because we are considering processes in the atomic level, while considering a massive amount of sample, there is actually statistics involved. But we will not discuss the statistics of nuclear reactions. For now, it is enough for you to understand that to understand what I just mentioned, everything on this slide. Okay? Okay, so radionuclides. So nuclides that don't undergo radioactivity or any nuclear reaction are stable, or we can also describe them as ground state nuclides. Oh, sorry. Okay, so we have uh, nuclides that do not undergo radioactivity. So they are just simply nuclides. And we also have radionuclides that are ground state. So they are not in the excited state, like what we saw here, the strontium that is in the excited state. No, they are in the ground state. They are ground state nuclides, but they are unstable, right? So they are unstable and they want to achieve stability. That's why they undergo radioactive processes, radioactivity, nuclear reactions. All of these are the same. Okay, so again, we have protons and neutrons in our nucleus. So there are strong forces, I mentioned this, provided by the neutrons. The neutrons sort of hold the protons together in the nucleus. So these strong forces, it's a technical term in physics, these strong forces hold the nucleus. They are attractive forces. And there are electromagnetic forces in the nucleus that are repulsive in nature. Why? Because we only have positive charges in the nucleus from the protons. So they feel electromagnetic forces, which are repulsive. They repel each other. So the balance between these two, the attractive forces due to the strong forces by the neutrons, and the repulsive electromagnetic forces due to the protons, determine the stability of a nuclide. So if the two forces are just, balanced, then we don't have a radionuclide. It's just a nuclide. But if one is a bit stronger than the other, it's not balanced, then this nuclide is most likely a radionuclide. It will undergo a radioactive process or a nuclear reaction so that it can be more stable. Now, if we try to plot our number of protons on an x-axis and the number of neutrons on the y-axis for all known nuclides. You will see that for those stable nuclides, those that do not undergo radioactive processes, they form this certain belt. It is actually called the belt of stability. Okay? All of the combinations that you see here, the number of protons and the number of neutrons for a particular nuclide, these combinations are stable. They don't undergo nuclear reactions. Any combination that is found outside, if we have that specific nuclide existing, then this nuclide is a radionuclide. So it can undergo a specific nuclear reaction so that it comes nearer the belt of stability. Okay? Another thing that we notice in this plot is that at low proton numbers and low neutron numbers, we see that they are almost equal, or in fact, they are equal, right? For very low numbers. But as we increase the number of protons, we actually need even more neutrons to provide the strong forces. That is why your belt of stability deviates from the x equals y line, this one. Okay? So, these radioactive processes, these nuclear reactions or radioactivity, can sometimes occur in a series. So there is what we call radioactive series. Again, it's because this is an attempt of a nuclide to reach the belt of stability. Okay, so an example, there are three examples here. Radon 226, molybdenum 99, and tin 113. So notice that the longest here is that of radium 226. So radium undergoes 6 steps in its radioactive series until it reaches lead 210. Lead 210 is found inside the belt of stability. It's a stable nuclide. It's not a radionuclide. Okay, so radium 226, the parent nuclide, and all the intermediate nuclides in this series are radionuclides. The daughter nuclide, again, is stable, so it's simply a nuclide, not a radionuclide. Okay, we see here another example of what we saw with rubidium 87, right, with the diagram. Here we see tin 113, okay? So it forms indium 113. Now this letter M here is, this means a metastable indium 113. So it's the same as the excited radionuclide, like what we saw with strontium 87 in the diagram here. 86, I mean, strontium 86, okay? So if you see M in the mass number, it means metastable. It's an excited state of a certain nuclide. So in the next video, we will learn about these nuclear reactions that I've been talking about so that we will understand this nuclear chemistry better.